This presentation will deal with HOMO and LUMO orbitals, the concept, and also with band theory. So our objectives will define and identify HOMO and LUMO orbitals, and we'll discuss the basics of band theory and why we care. HOMO stands for highest occupied molecular orbital. For this molecular orbital diagram, the pi 2p y star and the pi 2p z star are the highest occupied molecular orbitals. They're degenerate, so we list them both as HOMO. LUMO stands for lowest unoccupied molecular orbital. For this molecular orbital diagram, that is the sigma 2px star orbital. HOMO and LUMO designations become very important concepts when you make transition metal complexes. The gap between HOMO and LUMO predicts the stability of the complex. So larger HOMO and LUMO gaps result in more stable compounds. Lower energy configurations tend to be more favorable. So the larger the gap is, the lower the energy configuration, the happier the complex is. That's actually true for all molecules. They tend to want to have lowest energy possible. We're happy with low energy. All right, we're going to go over the basic idea of band theory. Solids have extended bonding networks. If we calculate the molecular orbitals for them, we are calculating moles of atomic orbitals into moles of molecular orbitals. So like 10 to the 23rd or more orbitals. Each bond has slightly different values for the energies. So if we put all of these together, it ends up resulting in a range of possible energies for each molecular orbital. The range of energies for bonding orbitals is called the valence band. The range of values for anti-bonding orbitals is called the conduction band. The distance between the valence band and conduction bands determined if a material is an insulator, a semiconductor, or a conductor of electricity. If the electrons are in bonding domains, they cannot move freely around the solid. The C of electrons in metallic bonding comes from electrons in the conduction band. The valence band is generally filled and the conduction band empty in these materials. So if we're in the ground state, valence band is filled, conduction band is empty. And this can relate back to our HOMO and LUMO designations. The valence band would be HOMO and the conduction band would be LUMO. But for band theory, we're specifically talking about bonding and anti-bonding orbitals. So this is not necessarily the case with the HOMO and LUMO band. The difference in energies between the valence band and the conduction bands is called the band gap of the material, labeled here. To promote electrons from the valence band to the conduction band, you have to add energy, specifically thermal or electrical energy. The larger the band gap, the more energy you need to add to make that transition. So the likelihood of making the jump is inversely proportional to the size of the band gap. Many electrons can make the jump from the valence band to the conduction band in conductors due to the small band gap. Very few electrons make it into the conduction band in insulators because it's such a large jump. That makes them poor conductors of electricity. And in semiconductors, we have properties in between, and their band gap is in between. The theoretical underpinnings for our understanding of materials for modern electronics, including solar cells, is in band theory. It's like it actually has its own journal to give you an idea of how big a deal this is. To summarize, HOMO stands for highest occupied molecular orbital. LUMO stands for lowest unoccupied molecular orbital. As an aside, yes, I know HOMO normally means same. This is the exception in chemistry. HOMO, highest occupied molecular orbital. In band theory, The extended bonding of solids leads to a range of possible energies for each molecular orbital. The range of energies for bonding orbitals is called the valence band, and the range of energies for antibonding orbitals is called the conduction band. And our conductors have small band gaps, which is the distance between our valence band and conduction band. Insulators have large band gaps, and semiconductors in between band gaps.